So you should clap harder because I am the person stupid enough to follow Sophie Wilson on stage. So I am Russ Olsen, and I'm here to talk to you about functional programming this morning. And the title of this talk is Functional Programming in 40 Minutes. And you might be thinking, oh my goodness, functional programming, it's a very complicated subject, it's very deep and everything. How is he going to explain functional programming in 40 minutes? And what I'm thinking is, what am I going to do with the last 10 minutes? Because fundamentally, I think functional programming is a very simple set of ideas. And if you just start at the beginning and work your way through the chain of logic that leads to functional programming, it's really pretty straightforward. I should warn you that I am a Clojure programmer, so my spin on functional programming is with a Clojure color, but most of what I'm going to say is just about functional programming. Every now and then I'll try and remember to say, oh, and this is how Clojure does it, but just keep in mind that's my bias. So the structure of the talk is I'm going to talk about what functional programming is, and that's going to be like the first 30 minutes. And then the last little bit of it, the last 10 minutes or so, I'm going to talk about what it's like to be a new programmer. You know, I'm just trying to adopt functional programming. What's that experience like? And then talk a little bit about, does it actually work in practice? So let's start with the what is it? And I should say that, I sort of got into functional programming, I don't know, about 10 years ago, and it was hard. It was like, you do the Google searches and things like that, trying to figure out what this functional programming thing is. And there was one thing that I read over and over and over that really was not very helpful, which is functional programming. Forget everything you know about programming, or even worse, functional programming. Forget everything you think you know about programming. It turns out that we know quite a bit about programming, right? And I'm here to tell you, no, functional programming does not mean you forget everything you know about programming. And in fact, if we sort of make an inventory, what do we actually know about programming? We know simple things like programs are full of names or identifiers, and you associate those with values. There's conditional logic, there's iteration, procedures or functions or methods or whatever. You have various data types, right? We are not going to forget all of this stuff when we go to functional programming. We are not going to forget about indentation when we go to functional programming. It doesn't change everything. Programs are full of namespaces, so our names don't collide. There's arrays and hashes or maps and things like that, other data structures. If you're doing classic kind of object-oriented programming, your programs are full of classes and instances and methods. And then finally, there's programs. And this is kind of my inventory of what everything I know about programming. Yours might be a little different, but we are not going to forget everything we know about programming. What I think functional programming really is a refactoring of what we think about programming, right? It's a refactoring of the way we go about doing programming. And so look at it this way, if you're working on an ordinary system, just some regular accounting system or something, and maybe someone designed it a few years ago, well, it's going to have a design, and maybe the design is not perfect, but it's okay. But over time, things change, you add things, you take things away, you start adding dependencies, right? You got to fix this bug. You add something new in there. After a while, you have what we in the business technically call a mess, right? It's just gotten messy. It's gotten kind of hard to do. And you're in this situation when somebody says, maybe there's a new engineer and they say, how do I do this? And you say, you do it this way unless this is true, in which case you do it that way. Or how does this work? Well, it works this way, except on Tuesdays, Thursdays, and Saturdays it works this other way. You know, we've all been there, right? It's not that the original people were stupid or the design is bad. It's just that the design has gotten messy and hard to deal with. So what do? Right? What you do is you start with a clean sheet of paper. I'm going to redesign this thing, right? I'm going to redesign my accounting system. And you start with this blank piece of paper. But not really, because the first thing you do in a redesign is you pull in everything that already works, right? Nobody really starts with an absolutely clean sheet of paper. Some of it works. Now, you're going to change some of it. Maybe you're going to throw some of it away. You're going to write some new things. But the problem isn't that everything is broken. The problem is that things have kind of gotten out of sync with themselves. And what you need is a new unifying principle. So maybe you add a message bus, I don't know, right? And you reorganize, redesign your accounting system, and now it works better until 3 years from now, the same thing will happen, but that's just life. So now, what about programming? And by programming, I really mean, what I have in mind is sort of the classic object-oriented approach to programming, like the stuff we all learned in school. Has that gotten messy? Is that in that like messy phase where we should rethink it a little bit? Well, I did a Bing search for object-oriented design, and I got 1.2 million results. And that tells me two things. Thing number one is that people are really interested in object-oriented design. And thing number two is there is no easy answer, right? Anytime you get 1.2 million documents talking about something, it means there isn't like a single place you can go to, there's the answers. Object-oriented design is hard. And you can also see some evidence that things are getting messy. If you just look at the languages, this is a line from the Ruby spec. And it's talking about protected methods, and it has that sort of ad hoc feeling to it, right? The receiver is always self, or an object that inherits from self, right? It doesn't have that feeling of clean and crisp. C++ is infamous for this kind of thing. Friend functions are functions that appear in the class definition, but are not part of the class. Or Java type erasures, right? This is one of my favorite ones. And again, I'm not picking on Java. I think it's the nature of object-oriented design, right? One thing I am absolutely sure of is if there's ever a monument to software development, right, maybe a giant statue of a keyboard or something, there'll be a plaque at the bottom of that, on the base of that monument. These words will not be on the plaque, right? This is not us at our best, right? So maybe we've gotten to the point with kind of our traditional approach to programming where it's got that ad hoc Tuesdays, Thursdays, and Saturdays feeling. So maybe it needs a refactoring. Maybe it needs a redesign. So let's start with a clean sheet of paper. And if I have any sympathy for the whole, forget everything you know about programming, it's this clean sheet of paper. But what's the first thing we do with our clean sheet of paper? We bring in everything that already works, right? Indentation works. Let's keep that. The comments work. Let's keep that. Let's keep identifiers and iteration and all the rest of it. The thing that is missing, the gap there, are the objects and the classes and the instances and the methods. That's the thing we're taking out, right? And we need something to replace it. We need a new organizing paradigm. And for that, we need to turn to our friends, the mathematicians, or at least if you're thinking about functional programming, we're going to turn to the mathematicians. Because I don't think we really spend a lot of time thinking about how the experience of doing abstract mathematics is kind of the same as doing software engineering. Have you ever been in that design phase of a new system where you're covering a whiteboard with boxes and arrows and you're having hours-long conversations with your colleagues and you're building this idea and you're building this other idea and you're trying to pull them together, right? And then maybe you build a prototype of your system and it's doing authentication and authorization and you've got it all wired together for the first time, and you send a message through it, and all the way at the end, it, I don't know, adds 1 + 1 to get 2, and you're like, yes, it works. It doesn't really do anything, but it works, right? The experience that abstract mathematicians have is similar to that. They build, they prove this, they prove that, they prove something else, and they're trying to pull it all into a bigger proof. Best example of that is this book. This is Principia Mathematica. It's written by 2 British guys at the turn of the 20th century, and it was an attempt to prove all of mathematics from very simple principles. And this is a huge book, and it is just covered with the most ridiculous math you have ever seen. It is way over my head. And it goes on for page after page after page until you get to this page. And there's 2 important things on this page. The first important thing is down there at the middle, and it is that. They have just proved that 1 + 1 = 2, right? It's the same. The second important thing is the page number. It's page 379. It took them 379 pages, effectively, of writing on the whiteboard to prove that 1 + 1 = 2. The point of all this is, mathematicians have some simplifying assumptions, and we can borrow one of them to make our lives easier. Put aside the question of whether we should be borrowing ideas from people who take 379 pages to prove that 1 + 1 = 2, but we can borrow the idea of a function. Now you say, well, gee, when we code, we have functions, procedures, subroutines, methods. It is not the same thing. A mathematical function is a relationship between 2 sets. It's a completely abstract idea. And each member of the input set is mapped to a single member of the output set. And that mapping is completely static. It never changes. So if you map 5 to 10, yeah, you can have a function that maps 5 to 42, but it's a different function, right? For any given input, you map it to the same output forever. Rain, shine, snow, sleet, it's always the same, okay? So how is that different from our methods, subroutines, procedures, functions? Well, our things are just code. They can do anything they want. So yeah, they can always return the same answer given the same input, or they can delete a file. They can return a random answer. They can do anything they want. They're just a chunk of code. So here is the fundamental conjecture of functional programming. And the fundamental conjecture of functional programming is, what if we imposed a set of arbitrary rules on our procedures, methods, subroutines, the things we call functions, to make them behave the way more like or as much like the mathematical functions as we possibly can. If we did that, would it make our coding lives easier? Would it make our programs easier to reason about, easier to get right? That's sort of the conjecture in the question. So what these rules effectively mean is that for a mathematical-like function, it can only look at its arguments, and it can only return the function result. There's no side effects. It's got to return the same result for the same arguments every single time. That's as close as we can get to a mathematical function. So no deleting the file, no updating the database, no writing the report or updating the user interface. Just look at the arguments and return a result. Okay. So what if we do that? So that's what I'm proposing that we put in place of our objects and classes and methods and all the rest of it. So does that really help? Would that really help us make our programs easier to reason about, easier to get right? Well, let's think about it. What if we had this simple bit of code, right? We have an X array, which is just 3 characters, an array of 3 characters, we compute y with one of these mathematical-like functions. People call these functions pure functions. I hate that term. I will use it, but I hate it because it's like it suggests clean and dirty or good and bad. This is just like an engineering decision, so there's nothing pure about it. It's like we're making an engineering decision here. People call them pure functions. So we have this pure function x, and we compute y. And for our purposes, we don't really care what y is. The question is, when we're done with this function, what is x? It's got to be the same thing, right? The rules say that you can't have any side effects. So we know that that function will not change the input value at all. So maybe that helps. But now, what if instead of calling a single one of these pure functions, we call this amazing mess of combinations of pure functions? And I'm telling you, they're all pure functions. They all obey the rules. Okay, so, and maybe this is 10,000 lines of code behind this mess of functions we're calling in the middle there. We're done, we compute y. What's x? It's the same thing, right? Those are the rules. You can't have any side effects. So maybe there is something here. Maybe there is something that will help us, right? I've just avoided reading 10,000 lines of code to assure myself that something hasn't changed x behind my back. Now that's something. But if we do impose these rules, now we have a problem. And the problem basically is that, you know, if in your language an array is mutable, and you can change it anytime you want, that means that we're kind of on the honor system here, right? I just told you these are all pure functions, but you know, short of reading 10,000 lines of code, what if somebody just slips something in there, right? And now I'm back to where I started, which is I have to look through 10,000 lines of code to figure out if my x has changed. So I'm going to propose a radical solution. How about if we make all of our data structures immutable? Once you make the thing, once you make the array or the hash or the set, you cannot change it, right? Well, that certainly takes the honor system out of this thing because you can't change the data structure. Now, you might be asking, well, how do I get anything done if I can't change my data structure? I make an array, how do I get anything done? What we do is we equip all of our data structures with a set of operations that are like, give me a copy of yourself that's just like you, only a little different. Hey, Mr. Array, give me a copy of yourself where it's just like you, except the third element is this other value. Hey, Ms. Hash or map or dictionary, give me a copy of yourself where this key is this value or this key is deleted, right? In that case, we can be assured that nobody's changing our data underneath us. It's like it puts teeth into the promise that these are actually pure functions. So if we do that, then we can be assured that our data is not changing out from underneath us, but now we have another problem, and that problem has to do with all those copies, right? And people usually, so I've got like a 27-element array here, but you can think of it as a million-element array, right? What if you had a million-element array and you want to change the middle element, right? So you make a copy of the million elements, and then you want to do it again. And you know, after a while, you've got several million elements floating around. That seems wildly impractical, right? It turns out that, no, you can do better than this. It turns out that some very smart people have come up with these things called persistent data structures, where here persistent does not mean saved to the database or saved to a file. It's just an unfortunate collision of the names. A persistent data structure is a data structure which is immutable, has these copy on modification semantics, but ironically does not actually do very much copying. And the way it works is there's one of these for all of the common data structures, hashes or maps and sets and things, but I'm going to talk about arrays because they're the simplest ones. What if behind the scenes you organized your array-like data structure as a tree, right? And I've got 3 element nodes here in this tree, right? And all the interior nodes, they just point at other nodes, and the leaf nodes have the actual data. So there's my 27 element array organized as a persistent data structure. Now, what if I want to change the middle element? And by change, I mean make a modified copy of this thing. Well, what would I actually have to copy? Clearly, I'd have to copy the node that the data is in that's changing. I'd have to copy the node that points it in, and I'd have to copy the node that points it in. And then I would not have to copy anything else because I can reuse all of the original. And so this is a way of having immutable data that you can that has these copy on modify semantics without actually doing very much copying. If you don't remember anything else from this talk, remember this picture, because this is the picture that makes functional programming practical, right? You can do this without a huge amount of copying. All right, so, and it gets even more practical. In my example, I'm using nodes that are 3 wide, right? Get it on the slide. But in real life, people tend to use nodes that are 32 wide. And if you have 32 wide nodes in a 3-level tree like I showed, you can hold 1 million elements in a 3-level tree, right? That's practical. 3-level tree, I can hold 1 million elements, and I can make modified copies without actually doing very much copying. All right. So along with the functions, my hokey icon for these persistent data structures is a lock. So we're adding that to our design. And now we have another problem, because I have just created this world where your programs are written with pure functions and they're using the persistent data structures, and maybe they're a bit easier to reason about and everything, and there's no side effects, which is what makes things easier to reason about. But our problem is this. Our problem is, well, if people still use business cards, I'd have business cards printed up that would have my name and just the word side effect on them, because we are all in the side effects business, right? Everything our customers care about is a side effect. You need the database updated, customer cares about that, that's a side effect. You need the report written, the web service hit, all of the things that we do in real life are side effects, right? And in fact, our customers don't think of them as side effects. They think of them as the desired effect. So we just built this programming world that, frankly, is lovely but cannot do anything. So how do we deal with that? Well, what we need are some bridges from our perfect, pure, functional world to the messy, side effect-y outside world. And so this is where I take the functional hat off, put the Clojure hat on. Clojure deals with this in a number of ways. Most functional programming languages have something similar. This is the way Clojure deals with side effects. One question with side effects is, what if I need some mutable data inside my program? And think of a web page with a hit counter, right? I need to be able to hold on to the number of visitors. Congratulations, you're the millionth visitor or whatever. How do you do that without side effects? Well, Clojure has these things called atoms, which are effectively variables. They're just variables, right? So they're mutable state. But the difference is the way you mutate them is you throw a function at your atom, and the function takes in the current value of the atom and produces a new value. So maybe you can increment the thing, and it's essentially a bridge. On one side, it's all functional. On the other side, it's messy and mutable and useful, right? So the other common solution, or the other common problem is, well, how do I do things to the outside world? How do I delete the file, update the database, this kind of thing? And a typical way you do that is you have a queue, and you put functions on the queue, except these are functions with side effects. And so in order, they get executed, and the side effects get executed in some kind of order. That's how you update the database, delete the files, or whatever. All right, and the idea is that you build your system that has so that it has a core of pure functions, of these mathematical-like functions that are relatively easy to reason about, and then around the edges you have these bridges to the outside world. And what this means is what you're doing is you are no longer using side effects as a tool to do your computation. You are perpetrating side effects at the end, kind of pushing them to the outer limits of your program. And the fewer side effect things that you have, the bigger that functional core, the happier you will be, the easier your program is to reason about. So that's the world of functional programming as far as I'm concerned. You have these functions that behave as much as we can make them behave like mathematical functions. You have persistent data structures which give the promise of no side effects, some teeth, and then you have bridges to the outside messy world of side effects and state and that kind of thing. So that's it. So that's my 30 minutes. I think I got that pretty good. So what is it like to work in a functional programming environment, especially if you're a new person? So let's talk about magic, and I'm here to tell you there is no magic, right? Anybody stands up here and says, I've got some magic for you, they are lying to you. There is no magic here. You can still have off-by-one problems. When I originally wrote this talk, I had spent 3 days chasing an off-by-one problem, right? You can still have off-by-one problems. You can still have redundant code. You can still have bad code, right? There's no magic. And the database can still be down. But your code turns out to be more threadable. It is more tolerant of threads. In particular, in functional programming, you tend not to run into the situation where, I've got one thread and it's in the middle of updating a data structure and another thread comes along and reads it and it's a mess. That tends not to happen. It tends to be the kind of thing you no longer worry about. Your code is testable, okay? If you have a function and you know that if you run an input value through it and get an output value, that is the output value it will always return. That makes your test easier to write. If you have a function and you don't have to worry if the database is up, if the data is just right over here somewhere in order for that function to function, your tests get easier. And your code is easier to reason about because there are times where you can just look at it and say, I know this part of it is just a bunch of pure functions, so therefore I know the following things, right? So you can reason about your code. So the actual experience, it's funny, I was walking in here today and saw the big GOTO sign. The experience of working in a functional style for the first time is exactly like back in the day when someone started saying GOTOs are a bad idea in your code. And the reaction to that was, how can I possibly work without GOTOs, right? How could you possibly write programs without GOTOs? Turns out it is possible. When you first start programming in a functional style, it feels like a pair of handcuffs. How can I possibly get anything done if I can't mutate my data in place? Turns out you work on it for a while, you sort of get your mind around it, and those handcuffs turn into a bicycle. They reduce the friction from where you are to where you want to be. So, does it work? Right? This is the $64 question. Does it work? Well, let me introduce you to Pedestal. Pedestal is a library of Clojure code, and it is the library in Clojure. It's one of the libraries in Clojure. If you're writing a service, right, there's always this library that routes a request to the right place. It maybe enables you to do authentication and authorization. It maybe does conversions. That library, there's one in every programming language, at least one. pedestal is that thing for Clojure. Pedestal is used in production code in Clojure all over the place. My last job, I worked at a bank, had 100 million customers, pedestal was everywhere. So it is a solid piece of production Clojure code. If you look at pedestal, it's about 10,000 lines of Clojure, which is a huge amount of Clojure. Clojure is a very dense language. 10,000 lines is a lot of production Clojure. If we look inside pedestal, pedestal has 21 of those bridges to the outside world, right? Just count them up. So it has 21 things that perpetrate side effects, maintain mutable state, that kind of thing. And it has 460 pure functions. So plot that on a pie chart, and that's what it looks like. Pedestal is 96% functional, right? So think about working on a system where 96% of your code is just functions that you can reason about, and 4% of it are messy things that are doing state, right? I think that's a pretty decent world to live in. Excuse me. So does it work? I think so. Yep. So that's what I had.